again for a second to talk about what we mean by factoring. Factors are things that are being multiplied together. So if we want to solve a quadratic by factoring, we are just trying to rewrite it in a way where we have something times something. The reason why we want to do that is this thing called the zero factor property. It says if A and B represent real numbers or real valued expressions, an expression is something with a number and a variable, like it could be like x plus 5, for example. That's an expression. If we know that A times B equals 0, then it stands to reason, right, that either A or B equals 0. One of them has to be 0, at least one, in order for when you multiply that they equal this, right? That makes sense? So basically it's saying, okay, if this is a true statement, then it's either true that this one is 0 or this one is 0. What we're trying to do is get quadratics where the A and B are things that look like this. Like maybe A is x plus 5 and maybe B is 2x minus 7. Because once you can write a quadratic in this form, you can, just like I said, A is 0, but here A is x plus 5. You could set that equal to 0. Once I set it equal to 0, what can I do next? Just solve it, right? X would be negative 5. This is the B part right here, the 2x minus 7. Similarly, I can set that equal to 0 and solve, and x would be 7 halves. So I would have two solutions to a quadratic, just like yesterday, but now we're just doing different methods. And so this is the zero factor property that says we can do that. Okay, I'm going to hold in that and say it later. So this is the, yeah, you're solving for x by setting it in factored form. And the reason why we call this factored form is because factors are things that are being multiplied. So we have x plus 5 is one factor times, right, they're being multiplied, 2x minus 7, which is another factor. So that's why it's called factored form. All right, so these are the basic steps for solving an equation using factoring. The first one is to move all the terms to one side and set it equal to 0. Second step, distribute or FOIL as necessary. Not all the problems you have to do that, but you have to check for it. Then you get to the factoring part. We're going to use either GCF, swing, or grouping. Those are our three main methods we're going to review today. And then the last step is to set each factor to 0 and solve, which I just talked about, on that last screen. These are the main factoring methods we're reviewing today. GCF, you factor out the greatest common factor from all the terms. Swing, find the factors that multiply to AC and add to B. Divide them by the A and then create factors with them. We'll review that here in a bit. And then grouping. It's used with 4 terms. You group 2 terms together at a time by using parentheses, and then you look for a GCF for those terms, and then you GCF again. And I'll be explaining all that today. So we're going to start with these 2 little examples. The first one is a review of GCF. That stands for greatest common factor. So the first thing we're going to do is factor out GCF. Give me just a second. I got to blow my nose. If you're looking at 6 and 18, you say, okay, what's the biggest number that goes into 6 and 18? 6. And then you look at the Q's and you say, what's the most Q's they have in common? 1, right? So it's 6Q. And so here's how I sort of tell students to write that. You're going to write the GCF down, which we said is 6Q. And then in parentheses, you're going to write the leftover factors. This is a reverse distributive property. So it's going to look how distributive property looks once we factor it out. So instead of multiplying something through to two things, you're dividing something out of those two things. So when you divide 6q out of the first term, what do you have left? Right, just q minus what 6q divided out of the second term? 3. 3. So that, we factored it, okay, by taking out the greatest common factor. We haven't solved it yet, though. So we set each factor equal to 0. So the 6q is like the A spot from earlier in the notes. So we set that equal to 0. And then the q minus 3 is like the B spot from earlier in the notes. We set that equal to 0. And then we solve those two baby equations. What do we do on the first one to solve? Divide by 6. So q equals 0. And then on the second one, we add 3. So you can box this form of your answer. You can write it in set notation if you like. I'm good either way. How many solutions is that? 2? Were we expecting 2 solutions? Yes. Yeah, because our power was 2, the highest power. The highest power tells you how many answers you'll have, or how many real number answers. All right, so that's GCF. The second example isn't really a factoring example. It's a solving example, but it's something we're going to use here in a little bit in another problem. You could technically factor this one, but I think square root's easier. So this one was our GCF example, and this one is our square root example. On the square root example, you want to isolate the B term. Before you take the square root of it, okay? So in order to isolate, what do I need to move over? The positive 8. So I do the opposite to both sides. B squared equals 4. And then what? Square root, right? So square root B equals 2. Ish. How many solutions is that? How many solutions am I looking for? So what did I do wrong? Plus or minus? Hold on one second. Okay. So grouping. How many terms do you think you see here? 4. So factors are things that are being multiplied. Terms are things that are being added or subtracted. And so there's 4 terms here. There's n cubed, 3n squared, negative 4n, positive 12. So when you see 4 terms, you will do grouping most of the time. And here's how we begin grouping. We group things. We group in pairs. So we'll group the first 2 together and the second 2 together. And that's how we begin. And then we take each of those groups and we GCF them individually. So GCF each group. So just looking at the first group and without hollering out, raise your hand when you think you figured out what those two terms GCF is. Raise your hand when you think you know. Okay. Thank you, thank you, thank you, thank you. Thank you, thank you, thank you, thank you. Oh, but you don't have to keep your hand up. I'm sorry. I just need you to like flash it at me. You have two hands up. Matthew, what do you think the GCF is? Yeah, who came up with n squared for their okay. So we write their GCF down, and we write the leftover factors in parentheses. Remember, it's like reverse distributive. You're dividing stuff out of each term. So if I'm dividing n squared out of these things, what's left over on the first term? N minus what? 3 on the second term. Take a minute in your brains and think of the GCF for the second group and raise your hand when you've decided what you like. Okay. Okay. So in my head, I can think of two things you've come up with, either positive 4 or negative 4. So who came up with positive 4? And who came up with negative 4? Okay. And it's not that either of those is wrong, it's just that one is better. The negative 4 is better. We're going to do that, and then I'll take a second to explain why it's better. But just trust me for 2 minutes. So if we are factoring out a GCF of negative 4, so we write that down. So I'm going to factor negative 4 out of these. So in that first term, what is negative 4 divided by negative 4? What's the sign on it? Positive, right? Positive 1. So that's a positive 1n. What's 12 divided by negative 4? So you might feel like, Ms. F, you just changed the signs on the things, and that seems like counterintuitive for a second. But it works because if you take this negative 4 and distribute it back through, what do you get? You get negative 4n right there and positive 12 there. And so at least the value is the same. Here's why we like this. Do you see how both of these groups now have an n minus 3? Okay. We're going to factor that out in just a second, and it's going to help us solve. Let me show you what it would have looked like if you had factored out a positive 4. I'm doing it in a different color so you know it's not part of my work, okay? If I had factored out plus 4 here, the negative 4n divided by a positive 4 would have given me negative n. And here, I would have had a plus 3. This negative n plus 3 is not the same as this n minus 3. So it's not that this is wrong, it's that it's not helpful for continuing the factoring process. Our goal is to get two things that match, because we're going to factor that out in just a second. This blue way doesn't help me, doesn't advance my cause. I just get stuck there. So if you ever start this way and you factor out a 4 and then you get the negative n plus 3, this right here is your clue. You need to change that sign on the GCF. Okay, so just be aware of that. That didn't really help. All right, so here we go. So now what we're going to do is GCF the whole thing. So looking at this term compared to this term, they have what in common? The n minus 3 in the parentheses. So that's their GCF now. So I'm going to write their GCF down. And I'm going to write the leftovers in parentheses. Okay. Once I divide out an n minus 3 from the first group, so that n minus 3 is gone, what's left over? N squared minus 4. Okay, n minus 3 out of there leaves me a minus 4. Now I'm in factored form because I have two things being multiplied. This is a factor. This is my A spot from the beginning of the notes. This is a factor. That's my B spot from the beginning of the notes. So now we set those factors equal to 0. And solve. So take a second and do that, please. Solving this one gives me n equals 3. Solving this one, I move the 4 over. I square root both sides, and I get n equals what? What kind of 2? Plus or minus. So there's my 3 solutions. By the way, if you're an insider's lie kind of person, you might feel like right here, you could have said that n is 3 and n is 4, right? Because you're like, oh, there's my factor of forms. I'm going to take the opposite sign. It's insider's lie. But that only works if this is a linear, it only works on linear factors where degree is 1. Because if it has a degree higher than 1, you have more work to do. So be careful about taking shortcuts like that you understand when the shortcut applies. Otherwise, it will lead you astray. It's a problem with shortcuts. There's like pros and cons. Okay, swing method. So here's the part of the lesson where you might have learned something different than this. Okay, but I'm going to show you how I'll be doing it. But everybody begins the same no matter what your method. And that first step is to get it equal to 0. So get your equation equal to 0. So you should have that, yeah? You move the 21 over by adding it. And then for swing method, here's how I like to begin. I give myself this little cross. And I want to figure out what 2 factors multiplied, or what 2 numbers multiply to AC and add to B. That's the same A, B, and C we talked about yesterday. I don't actually see an A value, so I know it's what? 1. So A times C is 1 times 21. And B is negative 10. What 2 numbers multiply to 21 and add to negative 10? Okay, negative 7, negative 3. Now, depending on what teacher you had or what you like to do, you might be used to doing this next. I'm going to do it in a different color and then erase it. So I want you to understand this is not the work I'm going to actually do. You might have done this. You might have rewritten the negative 10 and made 2 middle terms and then factored by grouping. Who's used to doing it that way? Okay. The way I'm about to show you swing, it's a shortcut. You don't have to like it. I'm not going to make you do it. But it's what I'll be doing at the board, so that's how I'm going to show you right now. And because it's a shortcut, it's like a little trick to remember. What I do from this step is take the A value. Those 2 numbers I got, I divide by the A value, no matter what it is. In this case, the A value happens to be 1. Well, dividing by 1 doesn't change anything. It keeps this as negative 3 and this as negative 7. And then my next step is I just slap negative 7 onto a z, and I slap negative 3 onto a z, and it makes my factors like this. Z minus 7 times z minus 3 equals 0. And now I just set those factors equal to 0 and solve. So set factors equal to 0 and solve. because those factors are both linear, and only because they're linear, you could right here stop and give me the solution, because you'd be doing insiders lie and just taking the opposite sign of those inside there. But only if they're linear factors. So you have to be careful about the insiders lie shortcut, especially when we get to higher degree polynomials. And we're going to do an example of what this looks like when we're dividing by something that's not 1 as well. Questions? Can I change this? Does anybody need it up anymore? Okay, here's one where that red step where I divided, the a is going to be different than 1, but starts the same. You have to get it equal to 0, so please do that. Raise your hand if you moved the v squared to the right. Anybody? Okay. Raise your hand if you moved the v and the 2 to the left. Okay. Both of those ways are fine. One requires a little more finessing than the other one. So let me show you what that looks like. If you moved the v squared over, you have this right now. And this is great because your a value is positive. But if you moved the stuff on the right to the left by adding it, you have this right now. And we don't like that because a is negative and it messes up our factoring methods. So, as a little side note, you need to make sure a is positive. Any suggestions for how I can deal with that? How can I make that -3 a positive 3? Thoughts? Multiply by -1, yeah. And you can either multiply through by -1 or divide through by -1. It doesn't matter, right? So I'm going to multiply by -1 by multiplying by -1. And you have to do that to both sides of the equation to keep it in balance. It doesn't happen to change the right side because that stays 0. And then I have 3v squared minus v minus 2 equals 0. The same as the other students who moved v squared to the right. That's what they have now. They just have it on the other side of the equation. But because they're equal, it doesn't matter. Okay, it's the same. So always be careful that your a is positive before you go on. And then this is how the swing method looks now. Okay, you still start with your cross. What multiplies to AC and adds to B. AC now is 3 times -2, which is -6. And B is -1. Right? There's no number written, so I know it's a 1. So take a second in your brain and figure out 2 numbers that satisfy that. And raise your hand when you have your 2 numbers. Yeah. What'd you get? What 2 numbers? Okay. -3 and 2. All right. So in red, I'm doing the divide by a step. A is 3. And now I have these 2 fractions, and I want to simplify them if I can, and one of them does. Which one of those fractions simplifies? The left one or the right one? The left. What is -3 divided by 3? -1. And then the 2/3 doesn't simplify, so I'm going to leave it alone. And now from this step, I make my factors. I say, okay, v with a -1 from that factor, and then v with a positive 2/3 from that one. Because those are linear factors, you can do insider's lie right now. And take the opposite signs, say 1 and 2/3. Or you could, which is a good practice, just set the factors equal to 0 and solve. Which is always good practice because you might be rushing and not notice one of them is not linear, like the square root one from before. And then solving gives you 1 here and negative 2/3 here. And even more information for you. If this was an SAT or a placement test or something that was telling you or asking you what are the factors or to factor it, you're probably not going to see answer choices where there's still a fraction in the answer. And that's where this name swing method comes from. If one of your factors still has a denominator, you swing it to the front, and this becomes 3v plus 2. And then you'd still have your v minus 1. And when you solve this, though, you're still going to get negative 2/3. You would set that equal to 0, move the 2 over, divide by 3. You get the same answer. So this way is faster, but all that other stuff, you know, is still just having a sense about what you're doing. Like a number sense, kind of. What are we at here, 325? How many more problems do we have? 0. False. Okay, we got 2 problems left, right? What am I looking at? Oh, we had a brain break. I know we're running out of time. Real quick with the brain break. Which bathroom do you know that show, the Mythbusters? Which bathroom stall did the show Mythbusters determine was the cleanest? The ones closest to the door, in the middle, or farthest from the door? Which do you think? Closest to the door? Anyone else? Middle ones? Those are the ones closest to the door. Because everyone assumes it's the most used stall, so what do? They skip it, which thereby making it the most unused stall, right? So it ends up being the cleanest one. So that show revolutionized the way I use the bathroom in public. I always use the first stall, which kind of creeps me out because people just keep passing it. And I don't know, maybe they're looking in the crack. I know people don't really do that, but it's like, makes me nervous, you know? Because you can like, what if they make eye contact with me or something? It would just freak me out. But it's the cleanest. Am I recording?
Yes.